Hey everyone, this video is about the ideal gas law equation. We will first speak about this equation a little bit and then we will try to simulate it in Python. So, hope you enjoyed this video, leave a like, subscribe, and let's go. Alright, so the ideal gas law equation is an equation that links the three parameters of a gas: its pressure, its volume, and its temperature. It is PV equals on RT, where N is the number of mole, R is just some, let's say, global gas constant. You see that it is called the ideal gas law. Why is the word ideal there? Well, it is actually a simplified model of how gases surrounding us behave, because you see that molecules can interact with each other, whereas in the ideal model, let's say, molecules interact only with the, let's say, the walls of a container. Now, what do we mean by that? The pressure in itself is defined with the number of collisions a molecule has with a wall. This is the ideal model. Now, in an actual model, in a real model, the pressure is defined with all the collisions one molecule can have, whether it's with other molecules or with the wall. Now, computing the number of collisions with other molecules can be quite difficult, in fact, whereas doing it with just the wall can be quite easy, as you can put sensors, for example, in a wall and directly measure the pressure they are exerting. Now, in the equation PV equals nRT, we can control the volume, the number of mole, and the temperature, but sadly we cannot control the pressure. So the pressure is actually a result of the three parameters right here. You can see that if we increase the number of molecules within a container, the probability of collisions will increase, so the pressure will increase. Again, if we reduce the size of the container, make it a very small container, for example, the space and the probability of the collisions again will increase, whereas if we make it big enough, the time where a molecule will collide with the wall will take far more time, so the number of collisions decreases immensely. Now, when it comes to the temperature, it is a bit interesting, since in a way the temperature is linked to the actual speed of the molecules. The higher the temperature of a molecule, the more is it excited. And the more it is excited, the more it moves faster. You can think of it as, for example, when you are heating oil on a pan. You see that the oil, when it's cold, is quite viscous, but the more you heat it, the more you give it energy, the more fluid and less viscous it gets. This is a bit an analogy, since when you give heat to a molecule, it is excited, it moves all around, like a little toddler making messy things, and it's the same thing with the molecules. If you heat it too much, it goes all around, and then the probability of collisions increases. What I want to showcase you with this Python simulation is how actually each parameter can influence the pressure, but also doing a simulation along the way. So let's get right into our Visual Studio Code interface, and cool transition. Alright, so hey everyone, we are back in our Visual Studio Code interface. We will start as usual by importing the two libraries matplotlib and numpy. So from matplotlib.pyplot as plt, and we are going to import numpy. Next, we are going to define our constants of the problem. By the constants, I mean first the number of particles, which will be equal to something, the size of the box or container, or the volume, surface, etc. Let's say we set it to container.size is equal to 1. We will mention the time steps, 1000, and we will define the speed of the particles. Particles speed is equal to something. Now, we will first start by, let's say, 100 particles, and then the container size will be, for example, 1 unit. This can represent 1 meter, for example. And then for the speed, we will choose something very slow for now. Let's say 0.1 meter per second, we'd say. Now we initialize the position of each of these 100 particles. We do this using the numpy.random module and package. So position is equal to np.random.rand. As you can see here, create an array of the given shape and populate it with random samples from a uniform distribution over 0 all the way up to 1. That's what we want. For example, 100 particles, then a size of 2. So 2 represents in this case the x and y coordinates. And then we do the same for the velocities. Now remember, here it is between 0 and 1, but we want each particle to have a random speed between 0 and 1 times the initial particle speed. So we are going to multiply this by particle speed. And same here, the position. Now we get a random array between 0 and 1, but we want to actually scale it to the container size. Now, since it's equal to 1, it's the same thing. But let's say it's equal to 10, for example, and then we scale it down, or rather up, to our container size. Alright, so the next step is to create our plot. So, creating our plot, like the usual way, I'll just copy it and paste it right here. So we create a figure and axis with the plt.subplots, like usual. We define a scatter since it is particles will be represented in a way as dots. So we use the x.scatter position x. This is all the x positions of the particles. This is all the y position of the particles. And we will mark them with an O. We set the limit between 0 and the container size, for example 10, for both x and y. And we set the aspect ratio to a box. So the x limit and the y limit will be the same. If I go ahead and run this code with a plt.show, I run. Now you can see this is the initial position of our particles without giving them any movement. Alright, so for now this is working. If I rerun the code, once again, you'll see that we get each time a new set of random positions, which is normal since we are using the np.random.rand. Alright, now running our main, so we do a simulation loop, like so, with double O. And then we say for step in range of our time steps. So in range of time steps, like so. Now we update the position of our particles. So this positions right here, it will be equal to positions plus equal velocities. So in a way, since we don't have an acceleration which is equal to 0 and a constant velocity, the position will each time be updated after each step. For example, if we will do here a little sketch at t equals 0, we have a position of 0 and 0 with a velocity of, let's say, 1, 0. Now at t equals 1, since this particle was in the position 0, 0 with a speed of 1 towards the x and 0 towards y, the position will be p1, 0 with still a velocity of 1, 0. And then at t equals 2, this will be the same thing. We will add this one with this one in a vector addition, which will be 2, and this speed will remain the same. So in a way, we are doing, let's say at t equals t, p of, I don't know, let's say p of t 0 is equal to p of t minus 1, 0 plus v of 1, 0. So in a way we increment it each time. This is why we're doing this right here. Alright, let me get rid of that. Let me hide this for now. I will show you what we will be doing. Alright, so if I rerun the code, and I forgot to show the plot, so plt.show. Alright, Let me cancel this and rerun the code. You see here our particles, right? For example, let's say this particle right here. We want to check if it is going to collide with the wall. If it's going to collide with the wall, it's going to bounce back, right? There's a pretty simple way for doing that. So let me close this, then redefine these and get rid of that. We check each particle, so for I in range of number of particles, alright, and then for j in range of 2, this is to check both the x coordinate and the y coordinate of the particle, and then we say if positions of I and j is lower than 0, so we exceeded the lower limit of the boundary, or positions of I and j are greater than container size. So in a way, what we are checking here is if whether the x or y coordinate is lower than 0, so the lower limit of our container, or it is superior at the greater limit of our container, we will do the collision. And to do so, we are simply going to switch the velocities. So velocity is equal, velocity of I and j is equal to -1. Alright. So here we define basically our simulation. Now remember, we need to update each time the position so we can see the animation. To do so, we do a scatter dot set offset. Did I define? Yes, set of offsets of positions. And then we do a plt.pause of 0, 0, 1, which is 1 millisecond. And finishing with a plt.show. Alright, we run our code. Now you can see here that it's a bit slow since I'm recording at the same time. But when a particle reaches the boundary, it bounces off. Alright, suppose now the mouse cursor is a particle, right? So suppose there is a negative velocity towards x, and a positive velocity towards y. So it will move like this. When it hits the wall, now when it hits the wall, it will bounce off like this. You know? Now here, the y velocity stays the same, whereas the x velocity will just be flipped, like so. Here we suppose that it's a entirely elastic collision, we don't lose any energy, which is not the actual case, but for sake of simplicity. Now, let me close this by doing a Control-C. To improve a little bit the plot, we can import matplotlib. So, and then we do a matplotlib.use tkagg. So in a way, this line of code is telling matplotlib to use the tkagg backend. In a way, it will improve our plot by balancing between performance and functionalities. You can see here we can drag it without it lagging, and we can also rescale it. Alright. Now you see that if we close the window, the code is still running. To fix this issue, we can, for example, come here and we check if the window is closed. So if there is a function in matplotlib called plt.fignum exists of fig number. So this line of code right here will tell you that the figure is existing. So if we add a not, so the figure is closed, we are going to exit our for loop. We rerun our code. You can see that we have the plot that is pretty much working. If we close it, the code exits. Alright, good. Now there is one thing I want to do with this code is to track the number of collisions. Now we can see, let me rerun the code. You see here, at each frame, we have a certain number of collisions. Now here the collisions can represent in a way the applied force of the particles on the surface or the walls if you want. And if we can track the number of collisions, we can have a rough idea on how the pressure is behaving inside this container. So if I close that, then I keep track of a collision counter. So let me define here collisions array is equal to an empty array. Alright. I initialize here number of collisions is equal to 0. Alright. And then inside of here, each time we have a collision, we are going to increment this little bad boy. Okay. Why am I saving it here? Because I want to display in a way the average number of collision after each step. To do so, I will do a collision array is equal to numpy.append collision array with number of collisions. Let me call it number of collisions. So here and here and here. And then we do a print statement. Let me just copy this directly like so. So what we are doing, we are printing the number of collisions, which is this one, and on average, we compute the average of this array. And then we do a R to delete the previous print and update it directly, so we have just one line of printing, not every time we see it here appearing one, and then another one, and then another one. Right, so let me rerun the code. Now, you can see here that on average we have 1, 2, 3 collision every time step here, and on average it is 1 roughly. Now let's try and change a bit the parameters here. We know that PV is equal to nRT. Now V here represents our container size, and well, N is equal to the number of particles divided by Avogadro's number. So in a way, N, the small n, is proportional to the big N, since the number of Avogadro is a constant, which means that our analogy to the PV equals nRT equation is here. So this would be N, this would be V, then time steps, well, this is just for our simulation, and then the speed. Now remember that the temperature and the speed are linked with the Boltzmann, are linked with the equation. They are proportional. So this in a way can represent the temperature. Let me do something like that. Kinda T. Alright. So remember here that if we increase the number of particles, the pressure will be increasing. So let's try here 1000 particle, so times 10. We rerun the code. Now you can see that on average we have 10 times as much collision. Previously we had, for 100, we had on average 1 collision every time step. Now for 1000 we have 10 collisions every time step, which is here, it is as if you multiply this, you replace n with 10 times n, and p will be also 10 times p, the previous p. Alright, so let me reclose that, and then let's say we reset this to 10. Now if we increase the volume, for example, I rerun this, on average we have 0 collisions, because they are so slow, they are moving with 0.1 meter per second over 100 meters. So the number of collisions is very, very slow. Alright, so we can see that by increasing the volume, the pressure is decreasing, which is also the case, since it is inversely proportional. Alright, so let me reclose that. Let's reset this to 10 and change the speed. Now remember, the speed represents kind of the temperature, since the more you excite a particle, the faster it gets. Let's say it is 2 meters per second. And we run the code. You can see that we have 20 collisions on average per time frame. Now, it is not very smooth, I get it, so let me close this. And let me set it instead to 0.5. Still not very smooth, but a bit better. You can see here that we have on average 4 collisions every timestamp. Alright, so this is a bit what I wanted to showcase with this small simulations about the ideal gas law equations. So the PV equals nRT. In reality, we can say that P is equal to nRT divided by V, since we can influence the volume, the temperature, and the number of elements inside our container. But influencing the pressure is a bit complicated, since it's defined with the number of collisions. In a way, it is defined with the force applied by the particles on the wall of the container. Now we cannot directly control the pressure without controlling these 3 parameters, so the N, T, and V. Whereas these ones, you can have a control on them, like we just said. So yeah, this is what I wanted to showcase with this small animation right here. Hope it makes sense if you had a bit of to the gas law equation. I find it quite interesting though to really see that the parameter, how they influence each other. So yeah, this is what I wanted to showcase with this little quick simulation. Hope you enjoyed it. Alright, so this is the end.
Hey, thank you for watching this video till this point. Consider leaving a like or subscribing. This motivates me tremendously to do even better. Check out my other videos if you liked this one. I got some Python tutorials, but also educational math. Hope to see you on the next video, and peace!